Great. So welcome everyone to our first lunchtime talk of the year. My name is Malena Cazorla Martinez, and I am the treasurer of the NUI SAG student chapter. So in today's talk, we have the pleasure to have with us Lisard Torró from the Pontifical Catholic University of Peru. He graduated in geology in 2009 by the University of Barcelona, and also in mining engineering in 2011 by the Polytechnic University of Catalonia. He obtained his PhD in earth sciences at the University of Barcelona in 2017. And ever since, his research has mostly focused on the lithogeochemical progressions of igneous rocks during the early evolution stages of island arcs and the contextualization of magmatic hydrothermal deposits within this tectonic framework. More recently, Dr. Torró and his team have been investigating the mineralogical expression, distribution patterns, and enrichment mechanisms of the so-called high technology elements in magmatic hydrothermal, and residual deposits in the Central Andes of Peru and Bolivia. So this is all from me. I'm gonna give the screen to Lisard. Please, if anyone has any questions, you can save them for the end of the talk, or you can write them in the chat and we will ask them ourselves, or you can also unmute yourself, but please after the talk. So please, Lisard, all yours.
Thank you, Malena, for the presentation. And well, in general, thank you to the National University of Ireland SGG student chapter for the invitation to give this talk. It's actually a great pleasure to me to talk about critical metals in front of an audience, including researchers from the IRIS Center for Applied Geoscience, who are indeed working in this same topic. And yes, during the next 50 minutes or so, I will be talking about three elements that are somehow hidden in the periodic table. They are somewhere in the periodic table, and they have picturesque names such as indium, germanium, and gallium. Their names might be picturesque, but the three elements are actually at the basis of our technological lifestyle, and also at the root of many green energy technologies that we will see in a minute. So I have divided this talk into two parts. The first part is mostly around, or talking about general aspects of indium, germanium, and gallium from a mineralogical and geochemical perspective, and then the second part, which will occupy most of my time, is devoted to explaining our research, our data on these three elements in deposits from the Central Andes in Bolivia and in Peru. So, as I said, the first part is about general aspects of indium, germanium, and gallium. And first of all, we all know that human development is marked by the use of increasing amounts of minerals, and this means in volume, but also in variety. Technological progress imposes the use of new and rarer elements. Okay, so this is the reason why I encourage my students in Peru to learn by heart the periodic table. All the elements there are becoming important for us. This is also the reason why we are witnessing that the number of elements that are reported in resources and reserves in many mineral deposits is growing. Okay. Since the number of elements in the periodic table is limited, what we do as humans, or Homo sapiens, is creating new alloys between elements. There are different international agencies who prepare lists of minerals or raw materials in general, some of them of mineral origin, which are important for their economy, safety. For example, the European Commission prepares a list of critical elements or critical raw materials, and which is in constant updating, in which a critical raw material is defined by being a raw material which has an important economic impact in the economy, and also, and coupled to this, an important or a high supply risk. So all the elements or raw materials that are beyond a certain threshold for the economic importance or the supply risk are cataloged as critical raw materials by the European Commission, including indium, germanium, and gallium. So why are they important? In the case of indium, it has many applications in technologies, since in the alloy, in the indium tin oxide alloy, ITO, is used practically in all flat screens and touch screens, such as those that you have in front of you in this moment, and also in photovoltaic cells. It's also important for the manufacture or in the LED and laser diodes industry and in batteries. You see that I have put here a cartoon with an Indian. This is just because the Spanish word for the element and for the native Indian is the same, indio, but the name of the element has nothing to do with this Indian origin, but with the indigo color, the blue color of the emission in the emission spectra. As for germanium, germanium is also widely used in digital technologies. It's basic for the manufacture of fiber optic cables and also plastics of the such as the PET, and is a semiconductor that is used in many electronic devices, just as gallium. Gallium is also a semiconductor which is used in integrated circuits and for laser light. It's also used in neodymium magnets to avoid corrosion, and is used in an alloy which is called CIGS, copper, indium, gallium, selenium, or sulfur, in thin films photovoltaic cells. So as you can see, the three elements are important for many technologies and are basic for this transition towards more clean energy production in the future. In the three cases, their demand is expected to grow in the next years. Here you see for indium, for germanium, and for gallium, but pay attention to cadmium. Cadmium is normally pernicious or considered pernicious, but its demand in the future is expected to grow a lot, also because it is used in solar panels alloyed with tellurium. So I put this here just because it is an element which is related to these three, as we will see in a moment. And the normal question then is, okay, Lisard, that's nice, but what about the price? How much does it cost? Okay, in the case of indium, this week the price was $400 per kilogram, germanium $2,200 per kilogram, and gallium $600 per kilogram. Just for comparison purposes, the price of silver now is about $750 per kilogram, so the same order of magnitude as indium and gallium. And you can see here that the price of germanium is at least 3 times the price of silver today. Okay. Some words about their geochemistry. Well, first of all, the three elements are very close in the periodic table. So they have in general, similar chemical behavior. Indium and gallium are metals. Germanium is a semi-metal or a metalloid. And regarding the geochemistry, their abundance is contrasting. For example, indium is an ultra trace element with content in the Earth's crust of 0.06 ppm, so it's an ultra trace. In the case of germanium, the content is a bit higher, 1.6 ppm, but for gallium, the content is much higher. It's 19 ppm. It's actually more abundant than lead. Lead is the next element in abundance in the Earth's crust with content of 10 ppm. As you can see here, also among other geochemical affinities, the three of them share this chalcophile affinity, which means that they feel comfortable in the structure of sulfides or in sulfide phases. And this is important because I will explain during this talk the occurrence of these elements in sulfide deposits. About their mineralogy, they form some minerals, that is, minerals in which they occur as structural elements, but they are only a few. There are like 12 elements, like 12 minerals of indium. The most famous one is rockesite of the chalcopyrite group. For germanium, we have germanite, argyrodite, and some tens of minerals. And for gallium, we only find 4 minerals in which gallium is a structural, including gallite. Instead, 3 elements occur as minor or trace replacement elements in the structure of major sulfides, such as sphalerite. As you will see, this mineral is able to concentrate quite huge amounts of the 3, and also in chalcopyrite or even galena. So they don't form many own minerals, and they don't form any mineral deposits in which the element, indium, germanium, or gallium, are exploited as the main commodity. They are always benefited as byproducts of other main metals in the same deposits. So, for example, one of the main producers of indium is Kip Creek, is a VMS in Ontario, in Canada, and the main commodities there are copper and zinc, and then as byproducts we have silver and indium. So this is the same for other types of deposits, as you can see here in this table. For VMS, we can find the 3 elements. For SEDEX, that I think are important for you, we can also find high contents, and also for MBT, as you will see, are very important for germanium, and it wasn't listed in this paper by Sankt in the 17th, so this is evolving continuously, and so on. So once we have defined this, I would like to move to the second part of the talk, which is about indium, germanium, and gallium in the Andes. So as you know, the Andes Cordillera is well-known metallothect for hosting a variety of mineral deposits, including many world-class deposits, with a variety also of metalliferous contexts which form in different mineral systems. Okay, and as you can see here, we have several metallogenetic belts where run or stretch mostly parallel to the coastline, and the distribution of these belts and the deposits, and ultimately the genesis of the deposits, is linked to the subduction of the Nazca plate beneath the western margin of South America. Okay, so in our study, what we have done is selecting some of these of the deposits belonging to different belts, such as in the Central Andean tin belt. Okay, and we also have other deposits that we have sampled related to porphyry systems, in our case, in porphyry systems, but belonging to polymetallic skarn or skarn-free mineralization, and also VMS and NBT belts. Okay, so let's see how these different types of deposits relate or correlate with the different technological elements that we are working on. Was there any previous information, any previous report about the concentration of these elements in Bolivia or in Peru? Yes, indeed, there was previous information, which most of the time is unknown to the miners. This is mostly the case in Bolivia, because if we go to the book Indium, that is like the Bible for Indium, we see that Wari Wari, which is a polymetallic polymetallic deposit in the Central Andean tin belt in southern Bolivia. This book explains that iron-rich sphalerite in this deposit contains very high indium contents with an average of 1 weight percent indium. That's a lot. And that from 76 to the 78, the Wari Wari zinc mine was the principal source of indium for the Indian Corporation of America, and when it closed in 78, caused a brief world shortage of indium. Okay, so there were previous reports. And for Peru, really not many academic work about, but if we look for the main producers of this element worldwide, we see that Peru is one of the main producers of indium. Okay, probably much higher than this, because they also sell concentrate minerals. This information is unknown for some of the mining companies working there. It's not unknown for the smelters. In the case of Peru, we have a very nice preview result obtained by Soler in the 80s. Soler studied the minor and trace element contents of ore from a variety of mineral deposits in Peru, polymetallic mineral deposits, and found different distribution of these elements according to the mineralization style, the geographic location, and very importantly also the host strokes. Okay, the problem with this nice, elegant work by Soler was that he studied a mineral or bulk or mineral concentrates, and therefore we cannot extract many or much information about the mineralogical expression of these elements, nor their spatial or temporal distribution. This is important because we all know here that in the deposits, the metalliferous content is normally zoned. For example, to put it more graphically here, in porphyry center or intrusion center polymetallic deposits, it is quite common that we have a copper-rich core close or next to the porphyritic intrusion that is followed outward by a copper zinc zone, then a zinc zone, and finally a lead zinc zone, and finally a lead carbonate zone. So the major elements, the major metals are zoned. The question is the distribution of indium, germanium, and gallium also spatially zoned? We will try to solve this here today. And the second question is the time. Okay, time is an important parameter. We also know that minerals, phases in a mineral deposit do not crystallize exactly at the same time, but rather during a certain time during the evolution of the mineral system, so that we have minerals that post-date or predate other minerals in the same deposit, in the same structure of the deposit indeed. And this is why we produce paragenetic sequences. This is very important part of our work, because we can have even different generations of the same mineral. So if we study this, what we have here in the screen now, for bulk analysis, we are missing also important information because we don't know how the content of these trace elements evolve during the evolution of the mineral system itself. So again, another question, is the distribution of indium, germanium, and gallium also temporally zoned? To solve this, of course, we cannot go for bulk analysis, but rather for in situ point analysis using electron microprobe or laser ablation ICP-MS. That's what we have done. To join the two questions that I have posted here, we took a large number of samples per deposit or district so that we could map the distribution of the samples along the district, and then also the distribution of the contents of the critical elements in these zoned districts. And then with these samples, we perform very thorough petrographic characterization. And once this petrography was performed, we perform only after the petrography the laser or microprobe work, because then we obtain results that could be contextualized, spatially and temporally. And this is what we have done. We have fun during the last 4 years performing this analysis. So let's begin with indium. We found some of the highest indium values ever reported in the Central Andean tin belt, and particularly in this deposit that is Animas. Animas is located in the very south tip of Bolivia, close to the Uyuni salar, which is probably familiar to you. And in this case, we found sphalerite with indium contents up to 10%. That's a lot, okay? And also in estannite with contents up to 4%. In this case, in this deposit, the content of indium was so high that we could analyze perfectly it with electron microprobe. But also even is that high that we could trace and map the content of indium with EDS, with an electron microscope. We found some interesting trends, such as these ones that you have in this figure. For a given vein, we found that the indium content increases with depth, or tend to increase with depth. The other important result of this research was that we observed a very good correlation between the contents of copper and indium at 1:1 proportion, which is also observed in these EDS images here in this below the slide. And this is very indicative of a couple substitution in which one atom of indium is incorporated in the structure of the sphalerite with one atom of monovalent copper, substituting two atoms of zinc. Okay, and we have observed this same trend again and again in many Bolivian and Peruvian deposits, and as we will see afterwards, it imposes some constraints on the distribution of indium at the district scale. So keep this substitution mechanism in mind. This is part actually of the Malena's final dissertation project in Barcelona. Malena was in the field and performed all this analysis, and in the field she could even learn about the local fauna in southern Bolivia. Okay, so let's move now to Peru. In this case, we will focus now in a polymetallic district, which is around the porphyry copper mineralization. So it's a porphyry copper system. Okay, in here we studied a polymetallic mineralization insist, polymetallic mineralization around a porphyritic intrusive, and this polymetallic mineralization was of skarn and epithermal nature. Okay. In the case of Morococha, as I said, we have this polymetallic district that is Miocene in age, and we have in particular one event of mineralization, which is referred as the Morococha district scale polymetallic event around the Toramocho porphyry. Okay, so here we have the Toramocho porphyry, and then we can see a distribution pattern that is very similar to the one that I graphically have some before, with a copper core followed by a zinc copper, zinc lead silver, and silver lead zones outwardly. Okay, so what would you do in this case? Of course, go to the different metalliferous zones and sample, and we did so. We performed sampling in low sulfidation polymetallic mineralization on skarn, in the case of Manto Italia and Codiciada. Then low sulfidation in the Porvenir skarn as well. And finally, in epithermal assemblages, we sampled high sulfidation veins that are telescoped, that are overprinting the Toramocho porphyry. So we have low sulfidation, now high sulfidation, and very important for the results in this study, also intermediate sulfidation in several bodies, mantos or veins at different distances from the magmatic hydrothermal center in lower Ombla manto, Morro Solar, Ibel, Rosita, Rubí, Isabel, and Ramal Alianza veins. Okay. So in this case, low sulfidation mineralization in Manto Italia and Porvenir skarns. As I said, is overprinting and skarn assemblage with magnetites, talc, serpentinite. And this polymetallic mineralization is composed of pyrotites, okay, low sulfidation, and high iron sphalerite, along with chalcopyrite and some other minerals. And in some cases, this pyrrhotite is replaced by a second step of mineralization of intermediate sulfidation with pyrite. But in any case, the chalcopyrite and sphalerite that we analyzed belong to a low sulfidation assemblage. Okay, then in the high sulfidation veins, overprinting or telescoped on the Toramocho porphyry, we found abundant pyrite and bornite, covellite, leuconite, and orgite that is typical of high sulfidation, and also chalcopyrite and tetrahydrogenantite, which means that at some point the assemblage turned to intermediate sulfidation and back to high sulfidation. In any case, here we also found sphalerite, but in this case is very low iron sphalerite or assembled with the high sulfidation stage. And finally, in the intermediate sulfidation assemblages, we have the case of lower Ombla, which are imposed or overprinted on skarn with magnetite. So we studied this polymetallic event with several generations of sphalerite and chalcopyrite. Okay, and for the Cordilleran type, we mean by Cordilleran here skarn-free polymetallic mineralization. We could observe how the first or previous states with pyrrhotite, this is, as I said, low sulfidation states overprinted by an intermediate sulfidation stage, including replacement by pyrite marcasite, showing these very nice I-bird textures, with, again, several generations of sphalerite and chalcopyrite, in this case, in intermediate sulfidation assemblages with pyrite. And when we go to the distal part of the system, we also find galena, tetrahydrogenantite, and also sulfur salt. And in this far or distal part, we have also siderite as the main gangue mineral. And even very late in the sequence, we have a botryoidal sphalerite. So remember, we are in a porphyry system. At the very end of the lifespan of the mineralizing system, we even crystallized sphalerite with these botryoidal textures, which are typical of other deposit styles, not of porphyry systems. But we will see that this is also important in this same slide. So don't worry about the number of data that is here in this slide. It's quite easy to understand. What we have done is plotting the different contents analyzed in a box and whisker diagram as it is classically done. And we separated the sphalerite. In this case, I will show only sphalerite because of time constraints. For sphalerite, we have these low sulfidation assemblages in mantos, which are, as expected, very high in iron. This is in skarn, sorry, a polymetallic mineralization in skarn, low sulfidation, high iron in sphalerite. Then we have the epithermal mineralization here in this part of the diagrams with high sulfidation sphalerite, which is very low in iron, and intermediate sulfidation sphalerite. So this is overprinting the porphyry itself, and these intermediate sulfidation assemblages are distributed in these diagrams so that these are proximal and these are distal. So we have an spatial control to observe trends in the distribution of indium, germanium, and gallium. You will see different colors for the boxes. Boxes with the same color belong to the same mineralized structure, be manto or vein. And you also see that for the same color, sometimes we have different, more than one boxes, each box belonging to a different generation of sphalerite, okay? So let's go then for indium. In the case of indium, the highest contents were found in the high sulfidation sphalerite, okay? In skarn is also quite high. We are talking about 100 or hundreds ppm. And in the case of intermediate sulfidation, as you can see here, the contents are very variable. What we can see is that there is a spatial trend towards indium depletion in sphalerite in the distal part of the district in relation to the proximal part of the district. Okay. Also, from early to late sphalerite generations. Regarding gallium, the distribution is quite or relatively homogeneous. Again, we see this depletion in gallium from early to late generations of sphalerite, and for germanium, the contents are very low as expected for a deposit of magmatic ascription. But in late sphalerite, we can see this huge increase in the content of germanium. This sphalerite is exactly this one, okay? So is late sphalerite, probably crystallized from very low temperature fluid, okay? So we also perform some more statistical studies, such as principal component analysis. Here also, again, only for sphalerite, in which you can see the skarn bodies are normally richer in the sphalerite in skarn bodies is richer in cobalt and manganese. This red arrow is indicating the spatial trends with these red dots representing the high sulfidation on top of the porphyry itself, okay? And this is the distal or the sphalerite in distal structures. And as we can see, we have a depletion in copper and indium from proximal to distal. And this green arrow is for the Yvette structure, the Yvette vein. And we can see that from early to late generations, there is an increase in germanium, which is the only element represented in the fourth quadrant here. Okay, so at least in sphalerite, we can trace some of the controls that are behind the indium distribution. First, we need, of course, a sourcing of indium via metal-rich magmatic hydrothermal systems or fluids, and we expect those to be located close or next to the causative porphyry. We also need a relatively high availability of copper because we need 1 atom of copper per 1 atom of indium to allow this substitution in the sphalerite structure. Okay, so we need both indium and copper. Those are transported better in high temperature mineralizing fluids with low pH to enhance the chloride complexes. Okay, so we also need availability of chlorine. Okay. Finally, in the case of high sulfidation assemblages, we can also introduce a fifth point that is competition for indium, because in this high sulfidation environment, sphalerite is a minor mineral. So there is few sphalerite in which the indium can partition. So if we have few sphalerite crystals, the indium will concentrate only in those tiny minor sphalerite crystals in there. Okay, I have described these trends for the sphalerite, but we also observed trends in chalcopyrites and galena. As I said, now let's move from porphyry system to VMS. In Peru, there is an important VMS trend, or here, as you can see, we have an important belt of VMS deposits. We selected some refined body in Maria Teresa. Is very close to Lima. Okay, this zone refined massive sulfide body includes a lower portion with pyrite and chalcopyrite and pyrite, which is followed by a zinc and a sphalerite rich middle zone, and finally an upper zone rich in galena and tetrahedrite. It's a classical zone refined massive sulfide. Okay, and the sulfides and the alteration assemblages are metamorphosed close to later dikes, and these have some importance in the results that I'm showing in this very slide. We studied the distribution of trace elements in chalcopyrite and sphalerite along a drill core that cut the entire body. So I will show again only results for the sphalerite. The contents of indium, germanium, and gallium are actually quite low, maybe except for indium at the 10th ppm level. Okay, but for germanium, for example, is very, very low at the sub-ppm level. Again, we found this substitution mechanism, including monovalent copper. And what is important here, and I will like to show you, is this diagram that we have with different contents of manganese, cadmium, copper, silver, and so on. So mineral elements in the structure of a sphalerite versus depth. So this is the depth in this drill core that cut the entire massive sulfide body. Okay, so we do observe a trend in the distribution, in the vertical distribution of these trace elements in sphalerite. So from top to bottom, we can see an increase in the content of manganese, copper, selenium, and indium. Of course, again, indium and copper following the same trend. Okay, and exactly the opposite trend for germanium. Okay, We could think that this is fortuitous, but if we use the geothermometer by Frenzel, which uses trace element contents in a sphalerite to trace the evolution of the temperature, we see that indeed these sphalerites are tracing an increase in the temperature toward the base of the massive sulfide body as expected, no? So we can rely on the results. Okay, so we propose that maybe this observation is useful during exploration in tectonized and even metamorphosed terrains. Okay, and finally, we have it all in Peru. We also have an important belt of MBT deposits, including the iconic San Vicente deposit. Okay, so we perform again the same strategy for sampling. This is the last study case that I'm going to show. In this, we focused mostly in Salipaico and San Vicente MVT deposits here. And in both of them, we observed a spectacular gamut of colors in sphalerite. So we focused our study in sphalerite. We see here hand sample pictures for sphalerite from San Vicente deposit, in which there is a first mineralization step or episode that is characterized by these zebra textures, also breccias, colorform arrangements, etc., with sphalerites that are black, yellow, brown, and yellow in color. And this mineralization episode was augmented by a second mineralization episode, which contains bright colored sphalerite with this very nice orange to yellow tonalities, and even white. I had never seen this before, no? White, silvery white sphalerite, which is very, very light. So we know from previous studies that germanium is normally very, or can be very high in MBT sphalerite. Again, here we see not one sphalerite. We could catalog up to 7 sphalerite types in San Vicente, and quite similar for Salipaico. So the question is the content of germanium and maybe also gallium temporally zone? Is there any particular different distribution in the contents of these critical elements between the different generations of sphalerite here? Okay, the colors of the sphalerite are very nice in hand sample and also under the microscope. Okay, particularly those are reflected light cross polar images. Okay, where you can see these nicely colored sphalerites due to internal reflections of sphalerite grains staring back at you. No? So with this information, with hand samples, with petrography, we could prepare this paragenetic sequence in which the different sphalerite generations are contextualized in the picture, in the evolutive picture of the deposit. So what is missing here now is knowing how the germanium content evolves between these different types of sphalerite. So that's the result. Okay, again, many data here in these box and whiskers diagrams, but you have to keep in mind, in any case here, that the color of the boxes here are similar to the colors of the sphalerite itself. Okay, so for San Vicente deposit, as I said before, we could differentiate up to 7 generations of sphalerite. Here you have from black, reddish brown, yellowish brown, orange, yellow, white. Okay, we have here the ones belonging to the first mineralization step. Here, these 3 belongs to the second mineralization step or episode. This is in the San Vicente deposit. We also analyzed some prospects, the Chilpes and Huacaras prospects. Okay, these are not exploited. This is exploited now. These are just prospects. And the Salipaico deposit, which is still inactive. Okay, So for germanium first, okay, from early to late generations of sphalerite, we can see an abrupt increase in the germanium content of sphalerite belonging to the second mineralization step regarding the first mineralization step, except for this white sphalerite, which is depleted in most elements, but not in all elements. Okay, in Chilpes and Huacras prospects, the contents of germanium are quite high and quite even systematically high. So in this case, keep in mind, these are prospects. These are not now, these are not being exploited now. So maybe the content or the high content of germanium could turn to be an important economical factor to take into account for the economic valuation of the prospects. Okay, and for Salipaico, which is another deposit, we have an increase in the germanium content from early to late generation. And what about gallium? In the case of gallium, we see again this increase in the content of gallium in the second episode sphalerite for the San Vicente deposit, okay? And quite variable for the rest of the deposits. So here we can see that not only that germanium contents are very high at the 10 and 100 ppm level and up to almost 2000 ppm. That's a lot. Remember the price of germanium a few slides before. But also we can see that it is temporally zoned, okay? And for gallium, we see that there is some zoning, but it's not that clear for all the deposits that we studied, only for the San Vicente. But if we focus then in germanium, we can preliminarily say that we could expect that germanium is higher in sphalerites that crystallized late in the paragenetic sequences and that are bright colored, mainly of orange and yellow color. And germanium is a chromophore element indeed, but I will not discuss this today. We would need another hour to discuss the color of sphalerite properly. So these are two important constraints now, okay? Higher in late generation, higher in bright color, orange and yellow sphalerite. What about temperature? As I said, we can calculate the crystallization temperature from the composition of sphalerite using the Frenzel geothermometer. And we see that the second mineralization step in San Vicente here, and that also germanium-rich sphalerites from these prospects in the San Vicente district, which were germanium-rich, formed at lower temperatures than the first mineralization step sphalerites, which are germanium poorer. So a third important constraint from this study is that lower temperature sphalerite that crystallized from lower temperature fluids as low as 50 Celsius degrees could be or are in principle germanium richer. Okay, we complemented this study. I'm finishing with this slide with a nano mineralogy using a transmission electron microscope, TEM, on electrotransparent foils cut with focused ion beam. Okay, in the different types of sphalerite. Okay, so we cut a lamella, a foil here. Here you have this foil, and with the EDS in the TEM, we could see and realize that the sphalerites are quite homogeneous chemically, except for the occurrence of some pyrotype nano inclusions in black sphalerite, but only in black sphalerite, and it's probably part of the reason of why this sphalerite is black. Okay, and in this case, this is the orange or sphalerite, germanium richest among the ones that we studied. Again, quite homogeneous coloration, so quite homogeneous composition. And if we go for high resolution transmitted electron microscopy, we see things like this. Crystal fringes, also at the nanoscale. Please note the scale here, 10 nanometers. We observe fringes, which might be due or are due in this case to polycrystalline matrix, but also to stacking folds because of different structures. Okay, and this is important because this was a surprise for us when we analyzed the structures of these sphalerites. Okay, in principle sphalerites, we found different polytypes of sphalerites, which is normal, but also different polytypes of woodsite. Okay, which wasn't expected. Remember, sphalerite is a cubic mineral, and woodsite is an hexagonal mineral, and we could determine, for example, the 10H polytype of woodsite. So I've been talking about the sphalerite during all my talk today, but at least at the nanoscale, we can also have woodsite, mostly in the germanium-rich sphalerite. And this is counterintuitive because, as I said before, germanium-rich sphalerite form at very low temperatures, and woodsite is the high temperature polymorph of sphalerite. So in the end, what we might assume is that the accommodation of this exotic element in high content, such as germanium, but not only, but including germanium, might trigger structural modifications leading to polytypism, and at high contents, even the crystallization of woodsite at low temperature. Okay, so just to put it more graphically, we have very high germanium content in this orange sphalerite here. Okay, we go to the nanoscale to 10 nanometers, and we did not observe germanium minerals. Okay, what we know is that this germanium is in the structure of a sphalerite. This is a very strong evidence that germanium is incorporated in the structure of a sphalerite. So as a final remarks or final notes at home, please keep in mind during exploration efforts, it's important to systematically analyze the trace elements in ore samples using commercial multi-element analysis packages, because you can have very nice surprises that will increase the price of your ore. These three elements, indium, germanium, and gallium, are chalcophile, and then might concentrate in sulfide deposits in which they can be exploited as byproducts. Different critical elements, including the three ones today, indium, germanium, and gallium, have affinity for different mineralization styles. So we have seen that, for example, germanium is more concentrated in low temperature, non-magmatic deposits as MBT deposits, and probably also SEDEX or Iris type deposits, while indium is higher in deposits with a direct magmatic connection and of higher temperature. Okay. Very important from this study, just as the major elements, copper, zinc, silver, minor trace critical elements are spatially zoned in intrusion-centered polymetallic system and in massive sulfide. So maybe with further study, we can use them as a vectoring tool. And just as major elements, copper, zinc, and silver, the contents of minor trace critical elements are also variable along different stages of mineralization. That means that they are also temporally zoned, okay, as we have seen for intrusion-centered, and then in the last slides for MBT deposits, okay? So all the data that I have put today here is published in these articles that you can download, or might ask for to Malena or to me directly and I can send all of them. Okay, and I have to thank also to the whole research team involving researchers from different universities in different continents, okay? And to the movie stars, the main characters of this research that have been the students performing their thesis in the framework of this project, which was financed by the World Bank and was performed in collaboration with these mining companies that you can see here. And that's all from my side. So if you have any questions, and if we have time, I know that I talk a lot.
I think it's fine. It was really interesting for me, at least. So actually, I have a lot of questions about that Woodside thing that you showed at the end. But yeah, we can discuss about that later.
Sure.
So yeah, if anyone has any questions, they can just type them in the chat or just open your cameras in your mix.
Just you can see here my email. So just if you want to write me directly, we'll be happy to answer.
Yeah.
I have a question. Julian Manouche here.
Hello.
Hello there. That's an awful lot of interesting data, and I think at one stage you were pointing out the substitution of indium into sphalerite, and it seems to depend on at least one other rare metal being available to substitute at the same time. Is that right?
Yeah. Well, by rare metal.
Well, I mean, not a common ore metal.
No, not always. In most of the cases, let's go for example to this one. No,
yeah.
It's coupled to copper. Copper is higher in certain parts of the districts. No, so copper. Other monovalent element which is commonly involved in these couple substitutions, mostly for germanium, not that much for indium, is silver, also monovalent silver.
Okay, but in this case, as you've written it there, it needs a trivalent ion as well.
Yeah.
Okay.
The
so
indium and gallium, for example.
You must have either gallium or indium in order to have germanium. That's right. Yeah. Okay. So that must be a very common constraint on how much germanium will go into sphalerite, is it?
Yeah. At least for indium, it's clear. If you don't have copper, this is less clear. But for indium, at least for gallium is less clear. But for indium, it's very clear. If you don't have copper in the media, you cannot incorporate indium in the structure. Exactly. Yeah.
Okay. All right. Thank you very much. Yeah.
You're welcome, Julian. Thanks for the question.
Actually, following on the same topic, I was thinking about why at the beginning you showed that some of the first studies that were done on indium in sphalerite, they were found, so indium was found in iron-rich sphalerite. But then we can see that actually in most of the deposits you've shown, it's the opposite. It's iron poor, and it's, well, copper-rich, let's say.
Thank you, Malena. This is an excellent question because we were initially convinced that only iron-rich sphalerite concentrated very high contents of indium, but this is not always the case, as we have learned during the last years. As you said, for example, in Morococha, the highest indium contents are in low iron, high sulfidation sphalerite. So, of course, we have much more data that I have not shown today. So, for example, we studied a deposit and recent discovery in Peru, which is Ayahuilca. And I think that you can see here, I had this slide, but because of time constraints, I just switched it. But look, again, different boxes for different generations of sphalerite. In this case, the red ones belonging to mantos, no? You can see here 3 generations of sphalerite. 2 of them are rich in iron, are low sulfidation sphalerites, and only 1 of them is iron-rich indium rich, sorry. So this one is indium rich and iron rich, but not all iron rich in the deposit is also indium rich, okay? So this is also an important question from a metallurgical point of view. If you ask a metallurgist about this, you can ask them, what do you prefer, an iron poor or an iron rich sphalerite for processing? And they will directly straight go for an iron poor sphalerite. Okay, so this could be maybe good news for them, no? That we also have high indium in iron poor sphalerite. Okay, but our initial data, and you were involved in this, Malena, in Bolivia, in which sphalerite is normally low sulfidation or in the limit with intermediate sulfidation, we were like somehow fixed that only this iron-rich sphalerite could host indium in high amounts, but we now know that this is not true. And as you have seen, iron is not involved in the substitution, in the coupled substitutions for indium. So this was an excellent question.
Okay. So actually those first studies, well, let's say that now we have evolved towards the fact, I mean, thinking that actually it's iron poor sphalerite, the one that hosts the indium, not the iron rich.
All of them.
So it was just like a belief at the beginning. Yeah, exactly.
All
so
of
it
them
was like a belief at the beginning. Yeah. Okay. Thanks, Lisa.
Welcome.
Yeah, Lingli, if you want to ask a question.
Yeah, thank you, Manila, and thank you, Lisard, for the excellent talk. Really nice pictures of the all minerals. I think I have two questions. One is about the indium, or probably more like comment. I think a lot of discussions on what controls indium, or let's say these critical metals, indium, gallium, germanium, sphalerite. For indium, they were saying like temperature might be really important, high temperature. But I think a lot of people now also think sulfidation is a very, very important, probably second order controls, except following the source of the metals. So I think probably, let's say, based on what we just discussed about the iron content in sphalerite, what it could say, it might possibly to say sulfidation really an important factor to affect indium incorporation in sphalerite. What do you think, Lisard?
Yeah, I don't really think that sulfidation is a key factor to the indium incorporation in sphalerite. As I said, we came to this conclusion after 4 years working on this, because at the beginning we were straight for the idea that indium was only in low sulfidation. There are more data that I have not put here, but we have other high sulfidation mineralization like in Colquijirca, in which you can see in Peru, you can see the low iron sphalerite intergrown with energite, and the contents of indium again are very, very high. So I think that the sourcing of indium from a magmatic source previous to its dilution is an important factor, not that much probably the, let's say, the amount of sulfur, no? Indium is also transported with chlorine, such as the same with copper. So we could not find this control, this sulfidation control on the distribution of indium. It is, of course, controlled by the sourcing of the metals, the availability of copper, the availability of chlorine. The temperature is favored, the transport of indium is favored by high temperature fluids, but the sulfidation is not only the temperature, so we could not find the straight connection between both indium and sulfidation state.
Okay, I think that's probably Andy's is excellent natural laboratory actually to understand this controlling parameter. I think my next question is germanium. What is the MVT in the MVT deposits? What are the elements like coupled to go with germanium?
For the substitution.
Yeah.
Yeah, mostly silver, but not only, but mostly silver. Again, is monovalent cations. Okay. And in this case, we found mostly silver.
Yeah, I think for the Irish one, we have copper, silver, both quite important, and lead and arsenic. I do also see you have lead arsenic mineral in the MVT deposit.
Yeah. Yeah. Exactly. Yeah. In this case, the point is that the copper content is so low in these MVT deposits that it's nowhere. So yeah. Silver is most important here. So this is different, of course, with the iris type deposit.
Yeah.
And yeah, we analyzed not only these two elements, of course, we analyzed many elements. I put only these two diagrams here in the article that was just published yesterday in Mineralium Deposita about this. You can find the whole set of elements. We analyzed also cadmium and many others, but these were not involved in the coupled substitutions. Yeah, so basically silver.
Okay, thank you very much. I will have a read of the paper.
Yeah. Thank you. And just as a side comment, as you can see here, germanium and gallium are decoupled here. So this is germanium poor and this is gallium rich. So they are not following the same trend. No, they can be perfectly decoupled. In some sphalerites, we discussed why gallium is not a chromophore element, at least in here, because this is white sphalerite, so no colored at all. No. Also for the rest of the elements. So this is discussed in this article that was released yesterday.
Okay, very interesting. Yeah.
Thanks.
Thanks
for the question.
Does anyone have any other questions? Well, I think we're a little bit off time, so
My fault.
I'm gonna stop here. But it was really, really interesting, Lisard. Thank you again. And yeah, if anyone wants to have any of the papers that he showed in the presentation, or any of the links, any of the data, I'm pretty sure you can just drop us an email, and I will contact Lisard, and I can just share all that information with you.
Of course, Malena, sorry, I interrupt. I can share with you perfectly this presentation, because all data is published. Okay. So I will send it to you.
Yeah, so if anyone wants the PowerPoint, just you can send us an email, and we will share it with you. And yeah, I will see you all in the next talk. And thank you everyone for coming, and thanks again, Lisard, for the talk and for sharing your experience and all your studies with us. Yeah, have a nice weekend.
Thanks, Lisard.
Bye. Bye.
Thank you. Bye-bye.